Hello there, and welcome to the fifth and next to the last in our 2008 series of summer lectures, which is sponsored by the Communications Department. We're going to be hearing from NERSC's Kathy Yelick today about the multi-core revolution in computing hardware, as it turns out, which wasn't what I had written down, but I think it's going to be kind of an exciting topic because of what the hardware has done to the software. Now I'm honored to introduce Kathy Yelick, who's going to tell us about multi-cores and the fallout from a hardware revolution. Dr. Yelick is the director of NERSC, and which is DOE's National Energy Research Scientific Computing Center, and she's a professor of electrical engineering and computer sciences at UC Berkeley. Her bachelor's, master's, and PhD degrees all came from MIT. She didn't arrive at Berkeley until 1991, and she joined Berkeley Lab in 1996. Dr. Yelick's career has been devoted to making parallel processing computers easier for scientists to use through the development of an array of a whole big number of software tools. She has provided apparatus for scientists and mathematicians in fields as diverse as symbolic algebra, blood flow to the heart, genomics, and integrated circuitry. Dr. Yelick led Berkeley Lab's Future Technologies Group and its contributions to computer architectures, operating systems, and especially libraries, including one that she and her students invented called Sparsity, which stands for, and which was the first automatic tuning library for sparse matrix computations. Since I'm not computationally literate, I can only imagine that a sparse matrix is one that looks more like tic-tac-toe than chess. But I think we'll maybe hear more about that later. Dr. Yelick's many services to the field include work on the National Research Council's Committee on the Future of Computing Performance and on DARPA's High Productivity Language Systems project. Among her many honors, teaching awards and best paper awards figure prominently, including the George Sprowls Award for an outstanding PhD dissertation at MIT. The newsletter HPC Wire has recently named her one of the people to watch. So it's a pleasure to welcome Kathy Yelick.
Well, thank you very much, and thank you all for coming. Let me start by just saying that I hope you feel comfortable raising your hand, and I do have a spotlight on me, so raise it vigorously if I don't call on you right away, but I'm very happy to answer questions throughout the talk. I'm actually not going to talk very much about NERSC today. I'm going to talk a little bit about some of the issues that we're worrying about at NERSC, but more generally about something that's happening throughout the entire computing field, which is multi-core processors. And I'm going to start by just talking about some of the hardware trends, things that have changed very dramatically in the last few years, and some things that have not changed very dramatically. So the first of those is something that I think there's some misconception about in terms of what is happening in the hardware industry, and that is there's something called Moore's Law that I'm sure all of you have heard of, which is the idea that transistor density doubles every 1.5, maybe 2 years. And so this is called Moore's Law, and it was named after Gordon Moore, who was the co-founder of Intel. And he made this prediction. It's not by any means a law. It's a prediction that the computing industry could sustain this kind of transistor density increase moving forward. And he made this prediction in 1965, and in fact, the industry has exactly been able to follow that trend line over the last few decades. So this has been kind of the foundation by which we have come to expect that computers will get faster and faster every couple of years. It is the reason that many people go out and buy a new computer, and so it sustains the industry because it's an industry in which you feel compelled to go out and replace your computer every 3 or 4 years because of the fact that the one that you have is so slow 3 years later. Now, Moore's Law is often, therefore, misquoted as being about computer performance. It's really not about computer performance. It's about transistor density. And this transistor density law is actually still alive and well. We have at least a few more turns of the crank in terms of transistor density, and we're going to be able to get more and more transistors on a chip every generation. So Moore's Law is still in effect. One of the effects of this is that we can put so many transistors on a chip today that in some sense the building block that we think of in building computers is shifting somewhat from transistors into processor cores. So the processor is now the new transistor. This is a picture of a comparison between a RISC processor in 1983, an Intel processor there in 1971, compared to a kind of a current processor today. And you can see that at this point you can put about over 2,000 RISC processors today on a chip, a processor chip size that we are building in the current technology. So the building block in some sense is now you can put lots and lots of these small processor cores, if that's the way we're going to build things, on these chips. Instead, a lot of the chip area is being taken up by other things such as caches. So this transistor density is continuing. So what is the revolution about? Why is there any problem at all? Well, I'm going to do this as kind of an old and new conventional wisdom. And the old conventional wisdom is that transistors are expensive and power is free. What you really worry about optimizing in chip design is how are you going to use those transistors on a chip. This picture, which is an old picture also showing a trend from Intel processors, is showing instead the power density. So this is the watts per centimeter squared of these processors. Now the problem is things looked okay over here, but we started following this trend line where the watts per centimeter squared was going up quite dramatically. So this is an exponential, this is a log plot over here. It's going up exponentially. This is some other interesting data points along that curve. If you follow it out, and you can see that we certainly cannot cool a rocket nozzle in a centimeter squared area of a chip. So the problem here is not that we can't put more transistors on the chip, it's that we can't turn them on. So it's okay to put those transistors, but as soon as you turn them on and you run them at a clock rate that allows us to keep scaling the processors in terms of their performance, the chips melt. We can't cool them anymore. So the new conventional wisdom is that the power wall means that we've got more transistors than we can afford to even turn on. So there's one sort of saving grace in here, and that is parallelism. So what parallelism is the solution to this power problem. And in order to explain why it's the solution to the power problem, I have one equation on here. This is still brushing over a lot of details, but just to give you a sense of why parallelism is helping with this power density problem, the basic idea is this formula right here, which is that the power consumed by these processor chips, or the dynamic part of the power, is proportional to this voltage squared times the frequency of the clock. So that's how fast your processor is running times the capacitance. Okay, so what happens if we put more transistors on the chip and we decide to use those to make the processor go faster? Well, what we do is we turn up the clock rate. And that's something that you can often do when you put more transistors on the chip, because the transistors get smaller. And when they get smaller, the length of the wires shrinks, and so you can actually run the clock at a higher frequency because it doesn't take so long for the signals to cross over the chip. So once again, from kind of a simplistic perspective, though, if we want to do that, if we want to increase the frequency, well, that's fine. We'll increase the frequency. That's going to push our dynamic power up. Unfortunately, to increase the frequency, we also have to increase the supply voltage, V, this term right here, in something proportional to the amount that we've increased the frequency. So rather than just getting a linear increase in the power, we're actually getting a cubic increase in the power if we want to use those transistors to run the clocks faster, to make them run faster. And there was a lot of hardware, the transistors in the past, that have been used to make the processors run faster, to sort of support the idea that you can run the clock rate faster. So if instead you say, well, the next time I double the number of transistors on my chip, I'm not going to run the clock speed any faster. I'm going to leave it the same, but I'm going to instead put twice as many cores on the chip. So I'm just going to copy that whatever was on the chip before and make 2 copies of it. Then I only have a linear increase in the power. And in fact, what we've seen in the recent years is not only have the clock speeds, these frequency numbers kind of leveled out, they actually dropped slightly, because the feeling was that in the hardware industry, they'd kind of over-engineered things in order to keep this kind of performance version of Moore's Law going. That is, the expectation that computers are going to get faster and faster, and they kind of went beyond the optimal point by trying to crank out as much as they could of the clock speed. So the problem is that we have to do things in parallel now in order to keep utilizing all those transistors. We also used to have a lot of hidden parallelism on the chips, and we still have this. There's some techniques inside of the processor, such as speculative execution. As I said, that's these are the places where you used all those extra transistors to make the processors go faster. Things like dynamic dependence checking. So what this means is things like speculation are running ahead in the instruction stream to try to figure out what's going to happen so that by the time you actually get to the point where you're executing that instruction, you're all ready for it. And instead, and then trying to, we need to push this parallelism. This was trying to automatically find parallelism in the hardware. Instead, in order to save power, we have to push this problem up to software. So the programmers, either those of you writing application programs or the compilers or some kind of a software system, is automatically going to have to discover the parallelism because it's too expensive to do it automatically in the hardware. So one way to think about this, if you're a user of parallel systems today, or any kind of computing systems, is if you want to continue getting the benefit of this increasing transistor density, which you've been benefiting from over the last few decades, then you need to be able to double the amount of concurrency you have every 18 to 24 months, about every 2 years. You need to think of a way of getting twice as many things happening in parallel. So that's your problem now. This is now a software problem rather than being a hardware problem. Kurt Koitzer, who's in the ECS department on campus, was involved in what's called the ITRS report or roadmap, the IT industry's semiconductor roadmap. And this is a group of very experienced people in the industry who get together to try to predict what's going to happen with performance of different processors. This is what that roadmap looked like in 2005. So in 2005, it said that out here we'd be somewhere close to running a gigahertz. Now, if anybody here has a gigahertz processor, I'd like to hear about it. As far as I know, nobody has built anything faster than about 6 right now. So we're well below what the expectation was in 2005. 2007, they went back and revised this roadmap. Remember, these are the experts in the field. These are people like the CTOs of companies that you all are familiar with, and they get together to try to figure out what's going to happen with this roadmap, and they've been very good at predicting it in the past, but they had to make this very significant correction in 2007 and said, we're no longer going to get this kind of clock rate increase that we were expecting. Instead, it's going to increase very slowly. So it's not quite flat, but it's going to increase rather slowly. Now, the other old conventional wisdom is that parallel computing is only for kind of the lunatic fringe, which probably many of you, if you're doing computing here at the lab, may be in that lunatic fringe, but it's basically the people who are doing high-end computational science. So the scientists who want to solve some of the largest computational problems are the only people that have been worried about parallel computing in the past. And as a result, it has not been a very lucrative field for companies to be involved in, whether it's a parallel software company, parallel language design effort in a research community, or in a parallel hardware company. So this was an article showing the Dead Computer Society, and roughly speaking, most of the parallel computing industry has, that people that tried to make money off of parallel computing in the past went bankrupt because there was just not a big enough market, because those of you here who do high-end computing are a very small piece of the computing market. So the new conventional wisdom is that parallelism is going to be necessary not just for scientists who are doing high-end computational problems, but for the entire information technology area. And this is a quote from a report that I was involved in writing called the Berkeley Review Report a couple of years ago, and Kurt Koitzer quoted this. This shift towards increasing parallelism is not a triumphant stride forward. This is not coming from a breakthrough because we've finally cracked the parallel computing problem. We know how to make it really easy to write parallel software and how to design parallel hardware. Instead, it is actually this retreat from the challenges that are faced in the hardware industry because they're unable to actually build these make traditional processor architectures go faster. So the hardware and software industry, surprisingly, and I would have to say even as somebody who was working directly in this field a few years ago, it was very surprising when suddenly the whole industry started shifting towards multi-core and started announcing we're building dual-core processors, we're building now quad-core processors, and so even within Microsoft, there was a lot of resistance for a long time within Intel and companies like that, and now they're all believe that parallel computing is something that they have to deal with. There's another trend that we often talk about, which is related to Moore's law, this increase in the number of transistors that you can get on a chip with each of the generations. This one is called Bell's curve or evolution of the computing classes. And part of what you're seeing, part of that is, there's sort of two pieces of it. The first one is that with each generation over time, you increase the performance, and not only do you get something that fits on the same chip, but even more importantly in terms of the industry and the market, it has the same cost and roughly the same form factor. So if you look at mainframes, of course the amount of computation that you can get inside of a fixed size, fixed footprint mainframe has increased exponentially over the years. What you can do inside of a workstation or what you can do inside of a laptop have also increased exponentially along with this Moore's law curve in the past. But the other thing that's happened is that if you look at more of this diagonal line, it says that the functionality, you can actually put things into a smaller and smaller form factor. So something that used to be a mainframe, you could put in maybe a desk side box. It became something that's maybe a laptop down here. Now it's inside of your handheld device. And then eventually it may be inside of, just sort of embedded in all of the systems in your cars, in your, inside of your systems, inside of your houses and things like that. So it becomes ubiquitous. So this is having an effect on the way the field looks at computing in general, which is how you kind of break things down between the different types of devices that people use. And what we call this is reinventing the client-server model. Google has the phrase which is the data center is the computer. So here's a picture of our kind of generic sort of data center there, which is a building-sized computer now. So these data centers are enormous systems that fill up an entire building. And then at the other extreme are the laptops and handheld devices, which are the client computers. And so here we've got some pictures of those different things. And of course, we've got things like the iPhone, which is a very high functionality sort of cell phone, and is taking over some of the functionality that people used to do on your laptop. So I don't know, depending on the age in this room, how many of you actually do more of your email or on your handheld devices than on your laptops or your desktop machines. But of course, people are getting RSI in their thumbs because they're doing so much text messaging. And I found that I recently bought my daughter a cell phone, and the first thing was, well, we need to get unlimited text messaging because they send hundreds of text messages in a month rather than a few of them, and rather than sending most of their communication by email or by phone. They don't actually use the phone as far as I can tell. They mostly just text message each other. So this is sort of an interesting model, and one of the questions and one of the topics that we've had actually serious debate about on the campus was whether the laptop will disappear as a device. So if you look at what has happened to some of the other kinds of mainframe computing systems, they've in some sense that middle group of computing systems have disappeared. There's these data centers, and now there's this idea of the cloud. If you've read in the popular press about the idea that there's these large co-location facilities where you have these computing centers, and so there's basically two computing devices. There's your handheld, your iPhone or your PDA, whatever, and then you have your computing cloud. And what's required in order to replace the laptop is an input device that's as easy to use as a keyboard, and an output device that's as easy to use as a screen. So those are the two pieces of the problem that I think still have to be solved in order to eliminate the laptop as a device. But there are certainly people working on them. So people are working on technologies to replace, to just say project a keyboard down, to be able to type on it, so you're just carrying around a little handheld device, and all of your data and your main computation is happening off in the cloud. So we used to also measure, a long time ago at least, computer systems by the floating point for performance, that is by the number of arithmetic operations that they performed. And this is the popular Linpack benchmark and the data taken from the top 500 list. These different curves, in case you haven't seen these over and over again, as those of us who work in the field have. These are the fastest 500 systems in the world based on this benchmark called the Linpack benchmark. It's a dense LU factorization problem. and which is a computation that's probably as easy to hit the highest performance in the machine as any other benchmark you can think of. There's maybe a couple of others that would be higher, but this is pretty much the thing that's most likely to get the highest performance out of your machine. People run this now in some cases for several hours or even over a day in order to get this benchmark number. And what you see here is the increase in performance over time of the different systems. So this green curve here is the fastest system on the top 500 list. This is the slowest system on the top 500 list, and this is the sum of the systems. And so this was one of the ways in which we have measured performance of these systems, and one of the ways in which we continue to, although it's recognized that this is really not the most important problem facing the future of these computing systems. Instead, the really big problem for performance is what we call the memory wall. And what you see here is the gap between this Moore's law and computing performance. Now, here I'm thinking of this computing performance as the entire chip performance. This slide is a little, you can see the graph is a little old. It was showing things at a time when CPUs were actually getting faster with Moore's law. Now the entire chip is getting faster in terms of its performance with Moore's law, but not the individual cores. But this gap still between the total performance on a chip and the total performance that you get out of memory, so this is our memory system, is a very large and growing gap. So what that means is that the most important thing to the performance of your computation is not how many operations you're doing in terms of arithmetic operations. It's not how many floating point operations. It's how many memory operations you're doing. So the entire way in which we teach computer science to undergraduates and graduate students today is typically, in terms of algorithm design, is organized around the idea that you're counting operations. And we tend to tell people to count arithmetic operations when, in fact, what we should be doing is counting these memory operations. So the other part of the memory problem is, so that's the bandwidth and latency problem, which is feeding these chips. So what the Multicore has done is allowed us to continue to hit that memory wall, which is trying to get enough data into the chip is going to be an increasingly important problem because we've now got all these cores in the chip and we have to feed them. Just as we used to have this problem of increasing the speed of each one of those cores. The other problem, which is a little bit more, which is not quite as dramatic, but is still very important, is that we used to grow the memory whenever we grew the speed of the computation in the system. So at NERSC, we always talk about balanced systems, so that we try to buy a system that is balanced in terms of the amount of computation it does and the amount of memory that it has, so that you can store large data structures in it, because that's what you need in order to do the computation. There is a technology problem, which is sort of turns into an economic problem, which is that the memory density is not increasing anymore as fast as processor density. So this used to be the growth curve for memory density. It was increasing by 4 times every 3 years, so on par with the processor transistor density increases. Now it's only doubling every 3 years. And so because of the fact that memory is not increasing in density as fast as the number of transistors are in the processor cores, we're going to have this gap in terms of the total amount of memory in the system versus the total amount of compute power in the system. So this means that we're either going to spend a lot more money when we buy a system buying memory, and at some point we can't balance that out, because once you've gotten to the point where you're spending 90% of your hardware budget on memory, you can't go much further than that. And so at some point it will be very difficult to buy systems that have the same kind of memory capacity relative to the amount of computation as systems do today. Let me skip that one. So the other old sort of conventional wisdom is that power is something that you only worry about if you're designing systems that are operated on battery power. So handheld devices, laptop devices, people that design those systems worry a lot about, and have always worried a lot about, the power that those processors consume. But today, there's a big concern not just about those battery operated devices, but also the systems that we run at places like computing centers like NERSC, or the data centers that Google and IBM and Amazon and so on have. And part of that is, if you look at the estimates for the total amount of energy that will be used by these large data systems and computing systems, in about 10 years, DOE would like to build an exascale system, that is 10 to the 18th floating point operations per second. And we just hit, if you've heard of the Roadrunner system, we just hit a petaflop, so that's 10 to the 15th. So another 3 orders of magnitude is the goal for about 10 years from now. The estimates for that are 20 to 200 megawatts. So that is, we're currently running more like 3 to 6 megawatts for our large systems, and we're talking about 20 megawatts as the very low-end target that people are trying to design for, and a lot of estimates that are well over 100 or even 200 megawatts for those systems. So this graph just shows kind of, it's a little bit of a cartoon, but it just shows that if you invest a certain amount of money in your system, let's say that you're going out and buying a $50 million computing system, and you keep doing that every few years. This is your fixed hardware cost, but the power is going to increase in a fraction of the cost, and it's increasing along these different kinds of curves. And this shows that eventually the power is going to completely dominate the hardware costs, and depending on sort of how far out you go and exactly what that growth rate is. So so power is now a big concern at the very high end as well as at the low end. And that's because the cost of the energy to run these facilities is going to be a dominant cost. Yes?
Is there a trend in the community to stop even talking about whether it's petascale plots, exascale plots, and start talking about memory?
Could I ask you to repeat that really loud?
Do you want me to repeat it?
Yes.
Okay. So the question is there any trend in the community to stop talking about petaflops or exaflops, that is the number of floating point operations per second that these systems do, and instead to talk about the total amount of memory that's on the systems? Is that, yeah. I would say there is not really much of a trend to try to do that. There is certainly a lot of concern about the amount of memory, but I was involved in a DARPA exascale study group, which was one of the groups that spent a lot of time looking at the hardware technology and trying to figure out whether it's even possible to imagine building an exascale system in the next 10 years. And it was pretty clear that with some breakthroughs in various technology and interconnects and some memory bandwidth technology, which people thought probably were likely to happen, that we could get to an exascale. But whether we can put enough memory onto that system to solve interesting problems is a really big question. So the community is aware of the problem, but I would say they have not yet started to switch over and talk about this is just a petabyte system and not worry about how many flops you can do on that petabyte system or that exabyte system. So it's a good question, Andrew. Okay, so just to summarize these trends, and then I'm going to talk a little bit about a project that's going on the campus. The power is going to be the dominant concern in these future systems. The big knob that we have for lowering power is to lower the clock rate and increase parallelism. So, to go along with lowering power, you have to always think about increasing parallelism. This memory wall is something we hit a long time ago. John Shelf likes to talk about this as the swamp. So it's not so much that we just sort of slammed into this memory wall where suddenly the memory wasn't fast enough to keep up with the processors. It's that we've slowly, with each generation, been walking into this swamp, and we're about waist deep already, and it's really hard to feed our processors at the rate at which they can compute on the memory values. So this has to do with both latency and bandwidth. And this problem might have stopped. That is, we might have stopped going into that swamp because we couldn't make the processors any faster. But instead, we decided to put multiple cores on the chip, so we still have the same problem now of every time we double the number of cores on the chip, can we feed those chips with enough memory? So we're still going into that memory, through that memory sludge. Memory capacity, as I said, is going to be an increasingly limited and costly part of the system. And probably the important point here is that the entire spectrum of computing needs to address the parallelism problem. So this is not just a problem for those of us who work on high-end computing here in DOE. It's an important problem. Handheld devices already have multiple cores inside of them. Laptops and desktops already, as you know, have multiple cores inside of them. I don't know how many of you have put your laptop on your lap recently, but you'll probably find that it's a fairly hot thing to actually sit directly on your lap. They need to crank down the clock rates to keep those things from getting so hot, and more importantly, from burning up power and using the battery life. And then in the high-end computing facilities, it's not so much of a power density problem, which is the chip level problem. It's the problem of how do you pay for the energy bill at the end of the year. And one of the one of the things that you can look at as either positive or negative is that those of us who do high-end computing are no longer alone in this, and so we may be getting more help from the rest of the IT community. Either that or they may be coming to us to look for help. So one final comment on this is that there's sort of this assumption that because the IT industry has managed to crank out all of these performance improvements in the past, that this one, which is the shift to parallelism, will just work as well and will manage to get all the performance out of these systems. It just means that all the software will be parallel. It is not guaranteed that this is going to succeed. Steve Jobs has said that recently that they're betting Apple is going to focus principally on this technology for parallel computing. So not only Intel and Microsoft and AMD, but also Apple is working on this. So it's not just a hardware problem, it's also a software problem. However, the failure rate of parallel computing companies is pretty close to 100%. With apologies to Cray and SGI, who are still around, there's a very long list of companies that failed trying to make money off of parallel computing. Now, as I said, part of the problem there was the only people buying those parallel computers were places like LBL, not the rest of the IT industry. So the market has shifted dramatically, which may make it possible for a lot more companies to succeed. But I think the real concern here is that problem that I talked about at the very beginning, which is why do you go out and replace your laptop every few years? You do it because it is so slow you can't even run the software on it anymore. That is the latest version of the software. If that no longer happens because that operating system and all those applications are only using one of the cores for the most part, then you won't have a big motivation to go out and buy a 16-core system when you've got a dual-core system already in your laptop. So if instead it goes from this growth industry to just a replacement industry, then the millions of PCs per year will drop. And what that means is there won't be money to invest in the technology. So there's this vicious cycle where we no longer have technology improvements, which are the things that sustained Moore's law, because we can't sell enough PCs because they're not getting faster. So that's the vicious cycle that I would say the industry is terrified about right now. So I'm going to talk very briefly about multi-core and high-performance computing. If I went by the number of workshops that I'm invited to these days on multi-core computing, this is the biggest problem that DOE is worried about in the Oscar office right now in terms of how they're going to shift all the users over to these systems that are built out of multi-core processors. They are not so concerned about the applications, the driving applications for these large-scale systems. I think it's safe to say that scientists, there are so many enormous computational problems that the scientists will always find ways of using these very large computational systems. Some of you were involved in writing this exascale report that came out earlier this year. Some of the applications that are highlighted in there that will require an exascale system are improved climate models, energy system models with economics built into them, biological system models, and this is just a few. And astrophysics, chemistry, all these other pieces of it are all big applications that have a lot of potential to scale. And since there's a lot of knowledge about those kinds of applications, I think, within the lab, I'm not going to talk so much about these kinds of applications, except to mention that I don't think we will have any problem using the machines if we can build a reasonable exascale machine. There are plenty of applications to use it. A bigger question is whether we can leverage what's going on in the hardware and whether we can leverage what's going on in the software solutions in the rest of the industry, because we're no longer alone, as I said, in this parallel computing arena. So I want to talk now about a project that's going on campus, although there's been a lot of involvement by people like John Schalf and Perry Husbands when he was here in putting this agenda together for what's now called the ParLab project at Berkeley. It was funded by Intel and Microsoft. That's a fairly unusual set of partners for a parallel computing project. It's also an interesting set of partners to work with. Just the two of them talking to each other is hard enough. You'd think they get along very well, but in fact, as soon as you get the lawyers in the room, it becomes very complicated. And we also have recently got some funding from the state through a program called UC Discovery. Dave Patterson is the lead PI on this project, and I'm continuing to be involved with it in addition to my projects up here. So this is the overall sort of architecture of the ParLab project. And the goal is easy to write, correct programs that run efficiently on many cores. Now, we use the word many core because we decided that the research problem is not really to worry about how to use dual core and quad core systems. What we really should be worrying about is how to use 64 cores or 128 cores on a chip, because you can see even in a conservative trend line that we're going to get up there within a matter of a few cranks of the transistor density Moore's law generations, and therefore right now, dual core and quad core systems are kind of justified by the fact that the operating system will run your browser on one of the cores, and it'll run your word processor on another core, and maybe your mail on another core. So for a few cores, we can get away with that, but you're probably not going to think of 100 different things to do multitasking that you actually want actively running on your computer at once. So we have to come up with other ways of using them. So this is the architecture. It has, of the project, it has applications, it has what we call the productivity layer, the efficiency layer. Most of the work is in the software layer, and then there's some research on the operating systems and the architecture layer as well. Correctness is a big theme that sort of cuts across all the different layers, and I won't try to tell you more about, I'll tell you a little bit more about what's in this software layer, but mostly I want to talk about the applications, because one of the comments that came out early on in the sort of multi-core, and then when we started talking about many-core, the idea that we should really think about the future systems, was people who would say, who needs 100 cores to run Microsoft Word? Why are you even working on this problem? And I think we think of this as the failure of the computer science education community to educate people who are forward thinking. So the question is not, do we need 100 cores to run Microsoft Word? Clearly we do not. The question is, what is the compelling application that will cause people to want to go and buy a 100-core system and do something really interesting or important or useful or something that makes lots of money, depending on your particular motivation, in order to motivate the users to buy a 100-core system. So when we stepped back to try to think about this, we decided, well, we're not going to look at coming up with a massively parallel Microsoft Word applications and similar things. Instead, we're looking at other applications, though, that we think are not high-end computing applications. Because as I said, I think those are sort of the easy case to make, that climate modeling will consume all of the cycles we can think of coming up with building. But the question is, what are we going to do to drive the consumer market? Because that's the technology that we're going to leverage in order to build the kinds of systems that we build and procure at NERSC. So we looked for applications that, first of all, had an enthusiastic application partner on the campus, so somebody that we could work with closely. It was a compelling application, either in terms of its social impact, it's in either short-term or longer-term feasibility. It required a significant speed up, so there was some argument that could be made, not necessarily that it was parallel, but that it could use more computational power somehow. And we also wanted to cover some of the different application areas, the handheld, laptops, games, consumer applications, and so on. So let me give you kind of highlights of the applications that we're looking at in this ParLab project, which, as I said, is specifically chosen not to be the kinds of high-end applications that we work on here, partly because with a partnership with LBL, we figured the campus project says these are well covered by all of the people working up at the lab on the high-end applications. David Wessel is a musician on the campus. He's a faculty member in the music department, although he's also he performs as a musician. He is very interesting in that he, as Dave Patterson says, we're a little skeptical that he's actually got his degrees in music because he's such a well-educated computer scientist as well. He claims that musicians have an insatiable appetite for computation. They want to have more channels, more instruments, more processing, more interaction. They have real-time constraints. So the rule in the music industry is if you have some kind of an instrument that's involved in a performance, you've got an orchestra of whatever kind, whether it's electronic or human, you've got to be on time. If there's a click in there, then that's considered an unreliable player, whether it's an electronic one or a human one. And the rule he has is 3 clicks and you're fired. So you can't be behind time, the schedule, and the real-time schedule if you're playing music. This is a microphone array that, speaker array that he built that has 120 tweeters in it. So one of the applications is a music enhancer, so something that gives you very high quality sound in a home computer kind of system, but also in, say, earbuds in a laptop and a handheld device. And then because we all spend too much time listening to those little devices, we also have to have something for people as they age, which are hearing augmenters. So these are things that are like a hearing aid accelerator. And one of the interesting observations is we all walk around now with these cell phones either in our pockets or attached to our belts or whatever. And so the idea is that the hearing aid is actually in that device, and what's up here in your ear is a little tiny thing. So these hearing aids are limited by what you can kind of physically put in the ear and doesn't look too obtrusive. And so you put just a little bit in here, and then they're, through Bluetooth or something else, are communicating with a much more powerful computing device that you wear on your, in your pocket or on your waist. So there are both sort of socially compelling applications as well as cool entertainment kinds of applications in this particular problem. The second one actually came to us from a project at Intel. They were also looking at future applications of Multicore, and this one is called content-based image retrieval. The idea is now that you've got a camera in your cell phone, you've got thousands of pictures that you take. Some of them are terrible and some of them are great, and you're trying to find things in them, and who has time to go through and actually label each one of the pictures with the people that are in that? I've tried to do that. I didn't get very far. The idea is that you can actually do queries on the photos in the image database by giving some example queries. So the query in this case is, I'm looking for a photo that contains these two people. And this is, I believe, Kurt's significant other and her daughter. And this is Kurt over here. But anyway, he's saying, well, it goes into the system. And you say, no, this is not quite right. And then there's some feedback in here. There's a learning algorithm. And out eventually pops the correct image. So this is a fairly sophisticated image technology. You're doing face recognition. But it's building, this is a personalized database, right? So this is not a large-scale, say, sort of commercial database. This is your personal database. Requires a lot of computation to both learn what's in the database and also then to be able to answer these kinds of queries. And the computational problems in here involve image processing as well as these learning algorithms. The third application is a health application, and the original version of it, and there's a whole spectrum of other things that are related. Tony Keaveney, who is on the faculty in bioengineering, mechanical engineering, and also has an appointment at UCSF in the surgery department, is the main PI on this application. The idea is to look at coronary artery disease. So this is a picture of your artery before and after a blockage. The idea is to try to not only do image processing on your arteries, but also simulation. So you simulate the arteries. This is blood flow through the arteries, so a computational fluid dynamics problem, which I'm sure there are many other experts in this room. A fairly complicated one because you have these elastic boundaries inside of here. And it's obviously a very important problem to try to detect these things ahead of time. There is a massively parallel implementation. There's a big finite element code that they believe can be adapted to solve this problem. It's been used in the past for bone density sort of simulations. But the idea here is not so much to replace anybody in the medical field, the humans, but to try to help with patient compliance. So rather than just telling somebody, you should take this medicine because it's good for you, you instead say, if you don't take this medicine, here's a simulation of what's going to happen, and here's a simulation of what will happen if you do take this medicine. So it's supposed to help the doctors with compliance. Then the last one here is what we call the meeting diarist and teleconference aid. This is Nelson Morgan, who is at the International Computer Science Institute, ICSI. It's associated with Berkeley. So I know many of you spend a lot of time on teleconferences, also in meetings. And the idea with a meeting diarist is that you have something that is recording the meeting. So here's a transcript. So it's doing voice recognition, turning it into a written transcript, but even more importantly then indexing it so that you can go back and find something that somebody said in the middle of this. So you can say, what was it that Kathy said about the Berkeley ICSI, and then you could find that in here and retrieve the text. So that's one of the applications. The other one is, and this by the way has to solve a very hard problem in speech recognition, which is speech within a noisy environment because these meetings tend to be noisy. The other one is a teleconference speaker identifier. So imagine the little screen on your teleconference phone that pops up and tells you who is speaking, because for those of you who spend time on teleconferences with more than about 3 people, it can often be confusing if you don't know the people well, especially to figure out who is speaking. Oh, and then the one last application actually is the parallel browser. This one we added a little bit later. And Ross Bodick from computer science is working on this. And why are we working on parallelizing a browser? The first question a lot of people have is, this isn't, what's important about this in terms of the performance? So Ross actually did some benchmarking of the parsing, rendering, and scripting of a, and I believe this was I believe this was a CNN page or another news page like that. And the question was, how quickly can you parse, render, and script that page? A lot of people think that on your handheld devices, the thing that's slow is the network. And it's true that the network is a limitation in there, but in fact, that's not the biggest factor. A lot of the performance delay that you see, so it's hanging up there trying to display the web page, and it's actually doing these other operations locally on your handheld device. And you can see that from the differences in the amount of time it takes to do that rendering and so on these different kinds of machines. So here's your iPhone here, taking 30 to 40 seconds in order to render that, whereas on your desktop it only takes 2 seconds. So it's not all about the network, it's also in the performance of the browser itself. And so he's looking at a new language actually to do this kind of, to specify the web pages that has more parallelism in it. So it's not just also about how you program that, it's how you even, how you encode the web pages themselves. And I think the other piece of this story is that a lot of people now treat their browser as their operating system. So their browser is their main interface to their computer. I was talking to somebody from Samsung yesterday who said, well, we want a browser on our TV because that's the thing that people are used to using. It's the interface to the computer. Okay, so the approach to this problem is to divide the programmers in the world into 2 groups. So we've got this big software problem, which is how do we write all of these applications in parallel now to take advantage of these massively parallel many-core systems with, say, 100 cores on a chip. And in order to do this, we thought a lot about sort of the breakdown of the programmers in the world. And the programmers here at LBL who program the NERSC machines are not even really this 10%. They're way down in there. They're probably about 0.2% or so of the program, probably even less than that. There's a few 100, 1,000 programmers that program these very high-end machines today. But in the broader IT community, there's still kind of the 10% programmers who are what we call the efficiency layer programmers. These are the people that we think we need to retrain to understand parallel programming and how to take it and what these multi-core architectures look like so they can take advantage of them. And they need to be able to get very good efficiency out of them. The second group of programmers are all the programmers out there, many of whom who do not have, they probably don't have a computer science degree. They may not even have a degree in any field. They're out there doing web applications by gluing together different software that other people have written, combining other frameworks and so on, and do not want to understand very much about the hardware. So this sort of breakdown, and there's different terminology that other groups use. I think Mort and Elvis is the terminology that Intel uses for the 2 different programmers. I think this one's these are the Elvises and these are the Morts. But the question is not should we think of the programmers divided into these 2 groups? I think the real question is it 90-10 or is it 50-50? Because if we have to retrain 50% of the programmers to understand as much about parallel computing architecture, software, and performance as the handful of people here at LBL and at the other labs that program massively parallel machines today, then I think the industry is really doomed. If we can get away with only retraining 10%, we can probably find that many people that we can retrain to understand this sort of expert parallel programming, and then the rest of the people will just build on top of the tools that others have built. One of the other sort of ideas that came from LBL, from Phil Colella, was a sort of organizing concept when we started looking at the application. So the history behind these are things called the Motifs. They were originally called the dwarfs for reasons that I'll explain in a minute. That came from Phil Colella. So about 3 years ago, Dave Patterson said to me, this parallel computing thing, I've been ignoring it for a while, but I think it's going to be really important. So how can we learn about parallel computing really quickly? And I said, well, we teach this graduate course. It takes a semester. You can go and take that course. But I said, you know, the set of things, concepts that we teach in terms of the different numerical methods that are used in parallel computing, in scientific computing today and high-end scientific computing is really fairly small. And there's this set of them that Phil Colella calls the 7 dwarfs. So the 7 dwarfs, and these are the things that are shown in red under high-performance computing here, are things like structured grid computations, dense and sparse matrix computations, spectral algorithms, so FFTs and other transforms like that, n-body particle methods, and something that used to be called Monte Carlo, which has now got renamed. But in any case, there were sort of a small set of things that we could talk about. And we could talk about the architectures that you need to support those computational patterns, and you could talk about the programming models and software that you would need to write. Now, people were pretty skeptical when we first started talking about them because they said, well, you guys are just doing high-performance computing. It's just about numerical software and scientific computing, and it's never going to drive the industry. What about all the other kinds of computations in the world? So over a period of about 2 years, Dave led a group that looked at machine learning algorithms, game algorithms, database algorithms. These are kind of desktop applications as represented by the spec benchmark, and then Kurt Koitzer's expertise, which is embedded systems. And the list grew from 7 up to 13. It got tweaked a little bit. It's not necessarily a perfect list. We can argue every time we sit down and talk about these about whether this is the right name for this one. But roughly speaking, you can see some structure here in the ways in which people organize their computations. And the important thing is it's not 500. It's not even 100 different things. And when we looked at each of these other areas, we didn't end up doubling the size of the list every time. We ended up adding a few more and having to think maybe a little bit more carefully about exactly what was captured in that set. Within one of these sets, there are many, many algorithms. So in structured grids, there's lots of algorithms. But it still gives you some idea of, when you talk about a structured grid, how you're going to compute over the data structure, what the data structures look like, and what the memory access patterns are going to look like, and if you're parallelizing it, what the communication patterns will look like. This is the set of ParLab applications that I talked about earlier, and the highlight of those with respect to each of these different categories of the motifs. So we did look at these applications, and you can see also that these applications sort of cover these different algorithmic methods. So how are we going to make it easy for the 90% of programmers to use these? Well, this is the most difficult part of the project, in my opinion, and the one that I'm most directly working on. We're trying to use an applications-driven approach, and right now we are looking at language that are specialized to music, to image processing, to the browser application, and to the health application, and I'm working on the health application language. We're also, in some sense, working on a bottom-up strategy, so we're looking at building software systems that work today on current multi-core and many-core systems by looking at GPUs and game processors in addition to dual and quad-core systems, and then from that experience trying to generalize across the language to a language that's both efficient and productive by building up abstraction levels. And then eventually trying to identify kind of a common language across these that will give us more of a general solution to the problem.
Kathy, I have to give you a 5-minute warning.
Thank you very much. So I'll just mention a couple other pieces of technology. So I mentioned that I'd worked on something called sparsity, which is a sparse matrix optimizing library that does self-tuning. So one of the other kind of key ideas that we're pursuing in ParLab is this idea of AutoTuners. And just to give you an idea of what an AutoTuner is, in some sense it's trying to get software to generate software rather than writing all the software directly yourself. Today, when you try to get performance out of a system at NERSC or one of the other high-end facilities, you can spend a lot of time hand optimizing the code to match the cache structure and the processor architecture of that particular system. So instead, the idea is that you generate lots and lots of versions of a code, usually used for just a small piece of code that is important in terms of the overall running time, and then you compile and run that, and you automatically then pick the best one just by running it and providing feedback. So there's systems that some of you may have used, FFTW for FFTs that do this. There's a system, Atlas, which was actually based on an earlier system here at Berkeley called FeedPack that Jim Demmel and his students built. And these are all systems that use automatic tuning. What we're trying to do is use automatic tuning in this sparse matrix area, which is much more difficult. This is a little kind of picture of a sparse matrix because the data structure is very irregular. A sparse matrix is one that only has a few entries, that is numbers relative to the total size of the matrix, and the data structure there becomes much more complicated. We call this is looking at part of this search space, which is looking at a blocking factor. So these are two different dimensions of a block size that you're picking within a matrix algorithm. And we call this the needle in the haystack picture because the temperature, the color here shows the speed, and here's the one that you want right here. And the point is not just that there's only one really good one. There's a couple of others that aren't too bad. Problem is that if you're off by just a little bit, you fall into a very bad part. So the optimization space is not very smooth. And for that reason, what we do is we kind of pick a piece of the optimization space using some performance models, and then we search over it. I will just mention that we're also working on some hardware work within ParLab. We're doing this with since we don't have access to lots of many core systems today, we're building a emulation system based on something called RAMP, which stands for Research Accelerator for Multiprocessors. The idea is to take FPGAs, so these field programmable gate arrays, which are reconfigurable logic, in which you can build a, say, 1,000 CPU system out of about 100 of these FPGAs, and we can then emulate this in hardware. This is much faster than a software simulation and allows us to experiment both with our own architectural ideas and also with other architectures that other groups are proposing. So that kind of, I think, summarizes the ParLab project. Since we're talking about various facilities up here and involving these projects, I also wanted to mention one of the things that's going on is what we call radical co-location, which is the ParLab project decided that, as I said, we picked application partners that were at Berkeley. We didn't try to find application partners that were at other institutions, although sometimes that can be politically a good thing to do when you're writing one of these big proposals. Instead, we're trying to not only get all of the people on the Berkeley campus, but all the people in one room. So we're actually tearing out the half of the 5th floor in Soda Hall and are rebuilding a lab there called the ParLab. And that is going to be almost completely open environment. Right now, because we haven't built it yet, all of the students and some of the faculty are sitting in what's called the Wozniak Lounge, which is a big lounge within Soda Hall with all their computers set up there. So it's kind of an extreme idea here to try to put all the collaborators together in one physical location without any walls, and to try to encourage collaboration and frequent communication, not just with the computer scientists, but also with the applications people who will have at least students sitting here if they themselves are not sitting within the shared space. So with that, I will end and see if there are any questions.
Very much. I tell you what, we got time for about one question, but people who do have questions after that can come and ask Kathy in person.
I have a lot of questions, but I guess I have to narrow it down to just one. Much earlier in your presentation, when you were talking about the power consumption increase that came with an increase in clock speed, and you were also talking about Moore's law and the increasing number of transistors for the transistor budget, it seemed to me like you were implying that an increase in clock speed means an increase in computational performance or power. But you'd already mentioned that that increased number of transistors doesn't mean increased performance or power. But in the same grain, increased clock speed also doesn't mean increased performance or power, correct?
Right. Well, so the word power here we have to be careful of. So an increase in the clock speed will mean an increase in the power that's consumed by the system. Whether it actually translates to an increase in performance for an application depends a lot on the characteristics of the application. It's one of the things that we do worry a lot about at NERSC when we're buying systems, is not to buy them based on the frequency and the total computational rate of that hardware system, but on how well they actually perform an application. So I'm not sure if that was your question.
Okay, we got time for one more. If there's somebody maybe on the other side there. Okay, you have another one?
Yeah, sure, why not?
Make it quick.
Okay.
It's okay.
Sorry. Okay. The other thing, when you were talking about multi-core machines or many-core machines, It's not necessarily one application that runs on each core, though. It would be a thread that runs on each core. Right? And if you actually open Process Monitor or hit Control-Alt-Delete on a PC and bring up the number of threads running, it's actually usually quite high. When I was running LabVIEW this morning, it was 100-something.
Sure.
So actually, there are some applications that do consume that number of threads, right?
Right, so LabVIEW is one of the applications, and there are some others, MATLAB, that are working hard at using many core and multi-core systems, so they will start many threads. It's also the case that you have lots and lots of threads on your system anyway, which are coming from all the different processes running around, worrying about whether you'd had email coming in and things like that. Most of those, though, are not actively using the processor at a given time. So within a system like LabVIEW, all those threads may be active, and that's because that company has already put a lot of effort into using many core and multi-core systems. There are a lot of other applications that aren't yet there, but you're right. There are a lot of threads running around. A lot of them are not actively using the processors unless the vendors have gone to some work to already parallelize them.
Well, thank you very much for a terrific view of the future. And remember to join us next week for Arun Majumdar.